can understand like this is the last session for the Connect and like everybody is busy checking out, so fine. So this is about like most of you like know how it works, specifically like Lava. I'll start with a bit of history on why we chose like LXC and then move forward from there. Maybe some of you here may not like be aware like how the LXC stuff works in Lava, so I'll just focus on that. So this agenda, so we'll have an introduction to LXC and why we consider LXC for Lava, and we'll see about the device type, the LXC device type, and we'll be specifically focusing on the Android testing use case, and then like a bit about like how it's been done in V2 and device dictionary and samples. So to give a bit of history, so we had we've been having like multi-node working, say 2.5 years or 3 years from now in Lava. So we started with that. Like when multi-node started, it was just started as a simple concept where we wanted to like submit jobs to more than one device, and then like the schedulers should take care of things in order to run these jobs on multiple devices. But as and when the use case grown, like for example, we wanted to support VM groups, and VM groups was the first use case, which made multi-node a bit complex. And after that, we also had other use cases in terms of like supporting Android testing. So it all grown in a way that multi-node was very complex. Like the normal or simple users of Lava weren't able to like catch up on that. So I mean, still like you would have seen on Riku's like presentation, like there are users who use multi-node, and it's only for the advanced kind of crowd who uses Lava, so that like they know what they're doing with the Lava send, receive, and all those kind of commands. So we wanted even a simple interface, and with all these things like with multi-node in place, like people can't like address some use cases specifically for Android testing. So Android required something else, because we used to have multi-node use cases solved by for Android testing in terms of having a KVM or an external device that talks to an Android DUT, and we had all these like allocation problems where the KVM exists and how do we connect to this specific DUT, which is in order to do Android testing. So then came this idea of using the NUCs, NUC kits, in between the DUT, that is the Android devices, and the dispatcher, so that we deploy whatever software that is required on the NUCs, and then like talk to the Android devices directly. But the NUCs and that solution was a bit like expensive, because we need to have apart from the dispatcher big machines, like we also need to have a NUC in between, because that's expensive, and then like talk to the devices. And each and every Android device should have a NUC, and that made things, maintaining things a bit costly. But essentially, if you see the entire picture, so the NUCs are nothing but a complete, which provide a complete operating system within as an interface to talk to the DUT. So like the idea came from the NUCs. Why don't we have a virtualized operating system within the dispatcher itself, which can replace the NUCs, so that like we can talk to the Android device directly. So that's how it started. So if you see like LXC devices existed, it started like 1.5 years back. It started its existence in Lava like 1.5 years back with the V1 dispatchers, where we had LXC support. But before like we wanted to proceed with the Android support with LXC in V1, we thought like it's better to do it in V2, because V2 had a better design in order to accommodate these kind of things. So that's how like we brought in the LXC inside Lava. So let me introduce what is LXC. So LXCs are nothing but like OS level virtualization, which provides as containers or a full-fledged operating system running within a host. So this is possible with two things which was existing in the Linux kernel. One is the C groups. C groups are nothing but it provides isolation for based on processes inside the kernel. And the other thing which makes LXC possible is the namespaces. So everything is isolated, and you have a sandbox environment which can run a full-fledged operating system. So before thinking about LXC, we also experimented on things like CH roots and SCH roots for the privileged and unprivileged kind of stuff. But they had their own problems, like talking to the devices or peripherals attached to the host machine was not so very well or very easy in terms of CH roots or different kinds of environment. So LXC made it transparent so that we can talk to the devices or the peripheral attached to the host machine in a transparent way from within the LXC container. So that's the purpose of having LXC. So from Linux kernel 2.6.24, we had the support for C groups and isolated namespaces. And one of the other things is the LXC containers use the same kernel as the underlying operating system or the host uses. So, and these are LXCs are very lightweight processes or lightweight isolated sandbox environment which gets started within the host. And we can also have our own network spaces, and there are huge number of network configurations that is possible and that could be implemented with the help of LXC. So LXC also has this privileged and unprivileged containers, and so as I said before, they have direct access to the peripherals connected to the host, and we can tweak things in a way that what peripherals has to be accessed and what should be shown to the container, and we can limit it to specific jobs. So that's a bit about LXC and the considerations which we took for Lava. The first one is multiple distribution. Lava used to do support operating systems or images such as Android, Debian, Ubuntu, and we have Open Embedded. So this was right from the beginning, but there is no point of there was no support for testing operating systems like Fedora or other CentOS or different kind of Red Hat based distros. So this is made possible, or LXC makes it possible for Lava, because LXC containers using the same underlying host kernel can run different flavors of Linux distros. So that is one consideration. And we also have multi-arch support. So LXC can, depending upon the kernel which is run on the host, whether it's an x86 or ARM-L or ARM-HF based kernel, we can use the same kernel in order to run the containers. And also we wanted a sandbox environment. So when we say sandbox, so this request came, is a usual request when it comes to Android testing in Lava. So what we need to do is some of the Android tests require different versions of Java or different versions of fastboot tools and the tools required in order to do Android testing has to be supported within the dispatcher, and it becomes impossible for people in the lab or the administrators in order to install different versions and maintain them in the dispatcher. And we didn't had a way to properly set up and scratch these things within the Lava dispatcher, and it also is not a good advice to have these kind of different packages, non-standard packages running within the dispatcher. So That would be made possible with the sandbox environment which LXC containers provide. And it's transparent and access to peripherals is there. And we also can do persistent LXC containers with Lava, but we are not supporting it yet because we don't have any teams or anyone who have a use case in order to have persistent containers. But that could be added, and it's a simple like option that could be added to the LXC containers in order to like support persistence. And so scratch hack boxes, that is also possible. Like instead of like giving hacking sessions on a device, we can just like fire up a container and then like ask people to use it, just to play around with how things work within the lab network and stuff like that. So there is also scope for future use cases like OpenStack testing because of the varied like configuration, network configurations which LXC container could support. Like we can do also OpenStack testing. So that is not yet like explored within the Lava development team, but there is possibility in future. So this is how LXC device type would look like. So you have, I mean, it's a normal device type as you would add a KVM or a QMO or any DUT under test. So as you said, like it aids in testing different distros. So you can like have an LXC template which says Fedora, and like you can like run your Lava test shell within that, and then like do testing on it. So this is the, the main purpose, as I said, for having these containers is to like support the complex use cases which came out of Android testing. So if you see in order to like get rid of these NUCs, we needed a mission or an interface in between the dispatcher and the DUT, and that could be possible with the help of LXC. Instead of, we had this thought of having a LXC device, just like how it used to work in multi-node. We'll, once a job is submitted, we'll bring up, we'll take an LXC device, which is on the same dispatcher as the DUT is connected, and then like talk to it. But later, like we evolved it in such a way that LXC containers could be brought up dynamically and then scratched, instead of like having a dedicated LXC device talking to the DUT. And then, so all the other LXC like features could be used in this kind of testing. So let me explain it in more detail with a schematic how it works. So as soon as a job gets submitted, so to the dispatcher, so there'll be a LXC container which will be like started dynamically within the dispatcher environment based upon like where the DUT is placed. So there is one single device configuration. We don't have two device configurations which says this is for the LXC and this is for the DUT. So the LXC parameters which are required for the device or the DUT which we use is part of the device configuration of the DUT itself. And it's a simple one-liner which adds this to the LXC, which I'll show you. So what happens is LXC container gets booted up, and then we can like talk to the device under test by exposing the device under test via to the LXC container. So in this case, for example, if you have like 5 Android devices connected to the dispatcher, so we'll try to like only expose the specific Android device which this job has to run based on. So that will allow, yeah.
So one dispatcher is connected with multiple devices, and whenever you submit a job for multiple devices, so every time there is a new LXC will be created for each device.
Yes.
Okay. So there is a load balance on a dispatcher, is it?
Pardon me?
I mean, Is it a overloading? Are you overloading the dispatcher by creating a LXC instance every time? Is LXC is heavyweight or a lightweight?
No, we are not overloading. It is like it is far, as I said, like LXC containers are very lightweight. Okay, and process gets started based upon needs. So it's not even like how we start a KVM device or QEMU device. It's even lighter than that. So still now we haven't got any problems in like running multiple LXC containers, but if there is a resource problem which arises, we can also like put in configurations, top level configuration for LXC saying this is the maximum amount of RAM or processor resources or the number of network devices that needs to be like allocated for each and every LXC instance that gets started. So that kind of configuration could be done, and so that's a possibility.
So here if it is a 100 device, so most of the things we use from fastboot and ADB. So if it is a fastboot connectivity and flashing the device, connected device, so if there are multiple devices connected to a single dispatcher, and dispatcher and LXC has to recognize which device it's going to, fast boot it and getting the things done.
Yeah, that's what I said, like it's transparent, and for this dynamic LXC containers which comes up, right, depending upon what job is getting submitted, only the DUT which is requested for that job will be exposed to that LXC container. Not everything which is there on the dispatcher.
So you are identifying the Android device through fastboot ID?
Yeah, the other thing with this is the LXC itself is cached on the dispatcher, so you don't necessarily have the same startup time. You also don't have any of the problems of trying to preserve this LXC. It is transparent so that you don't get any delays on that. So you would just install ADB inside. It is a normal test shell, the LXC, so you've got full access to everything you need to do to actually get hold of the packages you need or the code you need to run inside that. And then the jobs themselves are single node jobs, so you end up with you're just running, as far as you can tell, you're running the device, running the job on the dispatcher, talking to the device. It's just the LXC is in between transparently.
So consider it like this, like whenever a job is submitted, right, it is handed over to the dispatcher, and then the dispatcher starts another like small sandbox environment, which is nothing but a dispatcher on itself, which directly talks to a device. So it's a one-to-one like a dispatcher and a device talking to each other. Okay.
And the LXC only has that one device configured, so only that device path is added to the LXC. So fastboot and things only get to see that one thing.
In my job, do I need to explicitly say to install ADB packages, fastboot packages explicitly?
Yes, that will be part of your test job submission, because that's part of the customization of your LXC for that test job. Yeah.
Okay, so is there any default rules installed on a LXC?
LXC by default is a very minimal debootstrap. So it's the base system. So depending on the operating system, if you're using Debian, it's the main debootstrap environment. So you would know what that's got, and there'll be examples and things as well. So you'll just be copying these over.
Okay, so like that explains like how the LXC container talks to the DUT via USB connection. So we currently support ADB over USB for the LXC containers, and as said before, right? So only a single device is exposed to a single LXC container. So even if you're like doing even without a serial number, if you're using a fastboot, say devices or without -s option on the test shell, it is not going to like affect any of the other devices which are connected to the dispatcher. So, is there any questions on this?
I just want to make one comment. So, as with Docker, LXC also supports. So by default, so I think you guys are just creating a fresh container every time, right? So you can also have a container pre-created and then clone it instead of creating, instead of using LXC create every time. You can have a predefined container where you can pre-install everything you want. So you can have ADB fastboot pre-installed and then clone that container, and then you already have everything and don't need to install every time. That's how auto package test does that. So it creates a minimal container with the minimal stuff you need to test packages, and then every new test just clones that container and inherits everything that's already there.
And the container then is just supplied as a tarball or something?
Yeah, so what you do is you call LXC create first, then do whatever you want in the container, and then stop it, and then you leave it there in the LXC system containers, and then you just say LXC clone that container by that name, and with this new name, and then you start that new container, and it has a copy of the old one.
Yeah, the only complication with that, these are per test job containers, and so when the test job finishes, you blow away the whole lot. So it would need to be a way of, presumably once you stop the container, you can pack it up into an archive of some form.
I think what Antonio means is that, like for ADB jobs, create a container once and then have the minimal set of tools like ADB and fastboot there, so we don't have to install them. Yeah, exactly. So it's like after the job finishes, you just throw it away. But before the job starts, you have already stuff installed instead of installing it on the fly when the job starts.
That's possible. We could do that as a local distribution, because the moment you say unstable, Jesse or whatever, we could say, yeah, and have. But that then becomes lab specific. So you need to know that your lab admins have done that, and they will need to be done. So, but they can do that with salt states and Ansible things.
This LXC, so how scalable it is in terms of memory, I mean not exactly memory, storage, because I had to install Java, CTS and XYZ APKs on the LXC and just install on that. So
right now,
the storage of LXC.
Right now we don't have any configurations which is governing that, but it could be put on. It depends upon who maintains the lab and which instance it is on, and how we want to allocate resources for each of these containers. But that is possible. It's a configuration which needs to be done from whoever runs the lab. And
sorry?
It's again a dependency on the lab.
Yes, that's the lab issue. That's up to the admins, because a container isn't actually restricted on its size in the way that a full VM is. So you can actually have a container of a particular size.
But we can do that with the help of configurations. So we can limit the amount of RAM. Again, whoever is the admin has to decide whether a container should, say for example, if you have 8 GB of RAM on your dispatcher, at any point of time, each and every container should just use say 2 or 3 GB of RAM, not more than that. So you can limit that, and even you can limit the number of cores that goes or the container uses. So all these depends upon how an admin of the lab wants to restrict resources for each of the test jobs which goes.
And storage is open-ended because you don't have that problem. So that comes down, again, it comes down to the admin controlling the number of Android fastboot devices per dispatcher. So it's routine for the lab admins to shuffle devices between dispatchers as the load changes. And it's invisible as far as lab users are concerned. They don't matter, it doesn't matter. But that's a way for admins to do these kinds of steps of trying to make sure that you don't end up stressing out one dispatcher all the time with 15 LXCs. The main lab in Cambridge and Harston has got 17 dispatchers. And practice at the moment, standard practice, is that each dispatcher has a similar mix of devices. So you end up with only 1 or 2 of any particular kind of device on any one dispatcher. So it averages the load out. and then the rest is just down to usage patterns, normal admin status checks and things like that to see whether there are any problems with storage or with memory usage and other problems like that. But that's all down to the admins to sort out.
One more question. Can I SSH onto LXC and do a hacking session to connect a device? Is it possible?
Yes.
Thanks.
So, I mean, LXC, how it is implemented in Lava V2, it's a protocol, just like multinode or VLAN D, but it's a lot simpler protocol right now, which doesn't have many options. So, you need to, the protocol takes these kind of options. You specify a name for the container, temporary name, and then like there is template support. Right now, this template support is not robust enough. We support like two kinds of templates. One is the Debian template and the other one is the download template. So with the help of a download template, you can like possibly like install any kind of any operating system distros. But with the Debian template, like we just restricted it to Debian template because each and every template has its own options. I'll come to that, the disadvantages of having, some things in LXC. So basically the template takes in Debian and you can like specify which distribution you want, the release and the architecture. So if you are running on a different architecture and your host, there is a dispatcher host, supports a different architecture, you can specify that. And also we have added support for mirror and security mirrors so that you have a local Debian repository cached, so you can point to that. And so the containers are created from cache. So the first time the container gets started, it's going to take some time in order to pull all the packages out from the internet or from your cache stuff. But the second and third, the second invocation of the container is going to be really fast. It's going to take say 5 to 6 seconds for the entire container to set up and then go connect with the DUT.
And even creating the LXC the first time round is quicker than booting a VM and then installing the same packages inside the VM, because the VM itself is more or less the same mix of packages as the LXC, as the raw LXC.
Okay, and there is another concept based upon this LXC which came up, and it is not just specific to LXC, but it's going to be used across the Lava jobs. So there is this concept of namespaces which have come within the Lava job. So what these namespaces done is these namespaces ties different actions together. So say for example you have a deploy, boot and test action. So you can specify namespaces for each of these actions, deploy, boot and test, and then tie these actions together so that this is specific to an image which is getting deployed, and then the same image has to be booted, and then that has to be used for testing. So this could be done. We come up with this idea in order to specifically support the order in which things get executed. Even if you put an order if you're mangling with the order, say you have 2 deploys and then you say 2 boots. So based upon the namespaces, the Lava will try to boot the exact image which was deployed for the specific namespace. So that is one of the things which we came up with when we were working on the LXC containers.
And there will be examples in the documentation of how we actually use all these.
Yeah. So this is a sample Nexus device which works with a LXC container. So you can see this is the device dictionary. So apart from whatever is added as part of any other DUT, you can see there is settings for a device path. So the device path is the only stuff which will be used by the LXC containers in order to mask all the other devices and then just expose the DUT to the container. So this device path, right, it can accept a symlink. So if you have a UDEV rule which says, which creates a symlink for the devices, that could be put on here. Or it can also have a top level bus path which you can add to this device path, so that whatever USB devices are connected to that bus will just get added to the container. So that is also possible. So it depends, since this device dictionary is being done with whoever is administrating a Lava instance, so they'll have control over what has to be exposed to each of these containers. So, okay, this is how a complete device configuration looks like for the Nexus device. So you can see the device path is only a different setting apart from whatever we add to any other device in Lava. Okay, so there are some sample job runs. We are pretty sure the Nexus jobs, the Nexus devices are supported with ADB over USB on with the help of LXC containers in Lava, and it's been working for some time now, stably working for some time now. And we have some issues with the high key, nothing has changed with the implementation details which we have, but depending upon the high key images which is getting deployed, we have some issues. So the latest high key images which we have, that is build 147 or something, it doesn't work right now with this implementation. Basically that gets down to the images itself and not the assumptions and the implementations which we have done with Lava. So I'll show you a sample job, maybe. So this is how a sample job looks like. So you have the LXC protocol here, which defines a Debian template with the release as SID. And during the deployment, you can specify what are the packages you expect to be there in the LXC container. So for any Android job, we need ADB and fastboot, and Lava doesn't install it by default for you. So it is with the users. Users have complete control on what packages had to get into the LXC containers. And you can see the namespace in action here. So we have a deploy which says the namespace is TLXC, and this action, the boot action, will be tied directly to the deploy action. So this is required because we have some other deploy action in between and some other boot action in between. So you can see there is a test action which comes after some other deploy and boot action. So this test action will get mapped to the previous boot action and takes the prompts correctly. So that is the primary purpose of using the namespaces. So I'll show you a job run, how it looks like for an Nexus device. This one's staging, and it is working for a long time now. So it's a Nexus device. So we initially started with a Nexus 4. So almost like any of the Nexus device, if you have the right images, it should work with this LXC in V2. Okay. So this is how the container comes up, and we have worked. We have a patch which is going in the next release, which won't have all these details of LXC container, how it starts showing on the job log. And then
yeah, that's why we put the patch in, because it's quite long.
So here is how the overlay gets applied, and you can see then this is how the devices get attached to the container. So in this case, we have specified the top level bus Okay, this is a test or example job. We would just added top level bus without UDEV rules. So all the devices which is attached on that USB bus gets added to the container. And then what we do is we also do a fast boot deploy of all the images which you have supplied in your job. And as usual, the job runs through and it completes with the Lava test shell. So I mean, okay, that's a big file that got downloaded. Okay, so you can see it's basically a CTS job. So that runs talking to the DUT from the LXC container, and it completes properly.
Senthil, just go to the top of that log file and just show the total duration again.
Pardon me?
Just to go to the top of the log file so we can see the duration. Just press home as a min. There's a link to go to the top. Yeah. So that took 6 minutes.
This one?
Just yes, just a bit higher to show the timings at the top. Up again. There you go. So that entire job took 6 minutes, including all that logging of the output of the LXC and installing the packages inside the LXC. A lot of the Android jobs that involve V1 and multinode wouldn't have started within 6 minutes because they have to boot the whole VM, then synchronize, then do a whole range of things.
Okay, so let me talk about the limitations which we have right now. So basically the architecture support which I was talking about, it depends upon the underlying kernel which runs. So if you want to have ARML or ARMHF architectures to be supported, you need to have your dispatcher on that, or the host should be based, host kernel should be based on that architecture. And the other one is as we spoke, the distro templates. So right now we are using the default templates which has been supplied by LXC packages within Debian or Ubuntu or whatever. But we are planning to introduce our own custom templates so that it'll have an option interface which is unique across different distros. When I say unique, right, so you have, for example, in the Debian template, you say -- packages, and then you supply the list of packages that needs to be installed as once the LXC starts up. But in case of Fedora or CentOS, it doesn't work like that. And even there is a difference in how the Ubuntu templates work within the LXC container. So there is some, differences where we are not supporting each and every option which is there, part of each and every template within LXC. But right now we support Debian and download template. So we plan to expand it so that we can support even more distros as far as when we want to run Android jobs in specific.
The architecture thing you mentioned is not actually true. You can use foreign containers if you use QEMU user emulation. Also, there's a, so then you just need to include the QEMU binary inside the container, and there's a, I think there are patches in the upstream kernel to make that not needed, so you can have the emulation binary outside of the container, so you don't even have to include it, but it does work. I mean, you can boot a foreign container. How well that works, I don't know.
Yeah, so and as far as the initial use case of this is concerned with Android, there's very limited usefulness in the foreign architecture part, particularly as at the moment in Debian, the newest fastboot and ADB binaries in Stretch and Stable are only built for x86 platforms. But that's still going to be useful for other use cases where we need to do that. And it's also useful information for those who actually run lava dispatchers on things like kiwi trucks, because that is supported. It is a way of doing these kinds of things as well.
So all the links which are available on the presentation, like you can get it from the presentation and then like go through it.
Just one comment on the configuration part that confused me when I was trying to get this going is the seeming overlap between namespaces and method and connect in terms of trying to determine which one has relation with which one in terms of having multiple mechanisms in the same configuration file, and whether I should use connect or use the method, or whether the namespace was binding it. You know, specifically, I had the LXC container part to do fast boot, but then I had to use TFTP to download the overlay and to get that part going instead of, and mix the two. Huh? Well, this is the IFC that I was working on separately, but to try to mix them. And so kind of along that lines, if, you know, if it could get cleaned up in terms of what purpose exactly each one of those serve in terms of which parts it's going to bring in. Yeah. And along those lines, have you thought of moving to LXC the other deploy methods like TFTP and NFS and just standardizing on that as the communication method effectively with the device?
That would only be useful if you actually needed to have a different TFTP server, but then you could do that. At the moment, LXC is a special use case for particular purposes. We're still going to keep like the NFS server is probably better off under the main dispatcher, where we can monitor it and look after it more easily and track things.
So, I mean, the confusion which was created, that is because like we don't have any documentation for LXC right now.
This is true.
So, I mean, we'll address this and we'll put exactly like what parameter or what kind of methods or what kind of actions should be used for these things. So I'm just working on that, and one of the schematic which you saw, it's part of the documentation, so we're just evolving it. Like you should be getting it in next release, so that you have a clear picture on what are the actions and how to like specify the deploy. And even if you see on the deploy of Android images actions, you'll have the OS specified as Debian, and we have a specific purpose for that, and like we'll be explaining that clearly on the documentation. So.
Yeah, you've got a device that needs particular extra handling on top, which isn't the kind of device that we've actually been testing with so far. So we haven't even got to that point yet, right. Because we don't have the full support for the IFC 6410. So yes, that will be something that comes out in the course of the next release. We'll work all those issues out.
Okay, the other one is like whatever you saw here right now, like whatever is implemented and it's part of the releases, we just focus on the Android use cases. And if you are trying to like do a ADBO Ethernet and like expect things to work on the LXC container and talking to the device, it's not going to work right now. So that makes it in a sense like you can't like use the same jobs with a Ubuntu image or a Debian image. So Android image is the only thing which is supported right now. But in future, like we'll just get to it, where we can like pass the IP address back to the dispatcher and into the container, and then you can talk to the like DUT and test with a different image like Debian or Ubuntu.
Yeah, that's the main problem at the moment. Is so an initial fix for that is again lab specific, where if you have got the right device support, and usable MAC address handling, then you can give the device a fixed IP address, and then you short circuit the problem. But we're still going to have to actually look at how to do the identification of the IP address of the device that's just booted and get that information back to the dispatcher so that other things can talk to it. It's not a straightforward issue at the moment.
So that's pretty much what I had. Any more questions? Thank you.